Everyone, and welcome. Thank you for joining us for today's webinar, LLMs and Optimization Modeling Insights for Education and Practice. We are pleased to see participants joining us from across academia and industry for what we expect to be a timely and thought-provoking discussion on the growing role of large language models in mathematical optimization. Well, as LLMs continue to advance, many in the optimization community are asking important questions. How effectively can this model generate optimization formulations? What are the limitations? How might they change the way we teach, develop, and maintain optimization models? We're even starting to see big players in OR rapidly develop their own AI solution within this space. So in today's webinar, we'll explore these questions through recent research conducted at Kinaxis and the University of Ottawa by Negin Ayoughi and David Dewar. Their work examines how LLMs generate executable optimization models from natural language descriptions and analyzes the impact of doing so in a domain-specific language like AMPL versus directly using a programming language like Python. So during the first 20 to 25 minutes of the webinar, they will present their work, and following that presentation, we will move into a moderated panel discussion and audience Q&A to explore the broader implication of AI-assisted optimization, including its impact on education, industry, and the future role of modeling language like AMPL in supporting reliably this optimization and AI workflows. All right, so before we begin, let me just make a few housekeeping notes. So this webinar is being recorded and it will be made available following the session in our YouTube channel. And we encourage you to submit questions throughout the webinar and throughout the presentation using the Q&A panel. Ina from AMPL is with us, and she will help also organize those questions. All right, let me now introduce our speakers more properly. So Negin Ayoughi, sorry if I pronounce it incorrectly, is a PhD student in computer science and research assistant in the Sedna Lab at the University of Ottawa. Her research focuses on model learning for complex systems and problem domains, leveraging machine learning and generative AI to support system behavior analysis, verification, and decision-making. Over the past 2 years, in collaboration with Kinaxis, she has explored how large language models can help automate optimization modeling in supply chain planning systems by transforming natural language problem descriptions into solver-ready models. Her work aims to make advanced decision support tools more accessible to business domain experts. And David Dewar is also with us. He's the Director of User Experience at Kinaxis and a technology leader, product designer, and author with more than 2 decades of experience at the intersection of software, user experience, and innovation. Throughout his career, he has held leadership roles across startups and global technology organizations, including IBM and Cognos, contributing to advances in analytics, visualization, and enterprise software. At Kinaxis, he has helped drive the design of enterprise supply chain system and AI-enabled decision support tools. He's also co-author of the Addison Weasley Science Hub. Right, we are delighted to have you both, Negin and David, with us today to share your research and perspectives on this rapidly evolving area. With that said, I'll turn things over to you so we can begin the presentation.
Okay, thank you, Juan, for the introduction, and thank you for inviting us to the webinar. I'm sharing my screen. Just let me tell. Okay, hello everyone, and my name is Negin Ayoughi, and I'm happy to present our work on evaluating LLM-generated optimization specification with a comparison between AMPL models and Python code. This work is based on our paper, DSL or code at a case study in optimization at Kinaxis, accepted to the software engineering in practice track at ICSC 2026. Before I start the research presentation, I want to briefly introduce Sedna Lab at the University of Ottawa. The lab is led by Professor Shiba Nejati and Professor Mike Savedzadeh. The lab's research area is software engineering, and this project is part of our work at Sedna Lab in collaboration with Kinaxis. And I would like to pass it to David to introduce Kinaxis and share the industry context for this work.
Sounds good.
Yes.
Thank you, Negin. Thanks, Juan, for the introduction. Yeah, I've been in enterprise business software for decades, leading engineering and design teams. I'm actually now semi-retired, but at the time of the research, I was leading the UX team at the design team at Kinaxis. So I'll talk a little bit about Kinaxis just to give you a sense of the context of why we did this research. So Kinaxis helps companies manage and plan complex supply chains. So what does that mean? The clothing you wear, the food you ate today, the technology you're using, the transportation, the medication you take, all of these involve multiple companies working together to deliver that to you, and it can get really complex, and there's a lot of data. So Kinaxis brings that supply chain data together with planning, logic, analytics, AI, business optimization, all together into one decision-making environment. Kinaxis can answer many different business questions with really powerful algorithms. So I'll give you a specific example. Imagine a smartphone that you've got in your pocket, or maybe you're watching this webinar on your smartphone. The company that put that together to get it to you had to make a bunch of business decisions. And the first one might have been like, how many phones do we need to make by region, the stores they need to get to, can we make our launch date? Other types of things. Do we have what we need to make the phones? What do we need to buy? Do we need to move things from one place to another? Can we make our launch date? And maybe most important, the idea that things change, and can we handle any changes that happen after we've done our planning? So Kinaxis is an environment. It's a no-code environment aimed at business users. And what interested us was as AI and agents started to become more and more powerful, we wanted to know if we could make it easy for business people to create sophisticated business optimization models without having to learn how to code. We're going to present the work today. I'll pass it over to you, Negin, to continue with the presentation.
Thank you, David. Yeah. Uh, Kinaxis is a global leader in supply chain planning solutions. As David mentioned, Kinaxis supply chain planning software Maestro helps company plan inventory, production, and distribution in their supply chains. In these companies, business analysts often face decision problems. Consider this simple but important example. A planner facing a production planning problem. She needs to decide how many units of each product to produce and how to allocate limited resources to maximize revenue while minimizing the inventory cost. These users know the business problem well, but they may not have the expertise to build an optimization model. To solve such problems, analysts need a formal specification. This specification can be written either as Python code using a solver API or as DSL such as AMPL. AMPL has several practical benefits. It separates model from data, supports multiple solvers, and matches how domain experts describe the problem in natural language and mathematics. These features make AMPL a strong choice for this task. It's easier to review, reuse, and understand even for non-experts. However, writing these models manually takes time and expertise. LLMs can be used to derive these models automatically from natural language description. The question is, can they generate DSL as well as general purpose code? Since LLMs are trained on corpora that contain far more general purpose code, such as Python, than algebraic DSL, such as AMPL. To answer this question, we introduce EXOS, extraction and error-guided refinement of optimization specification. It's an LLM-based method that transforms natural language problem description into formal optimization specification in AMPL or Python. EXOS has 4 steps with a refinement loop. Step 1 structures the natural language description by extracting objectives, constraints, parameters, and decision variables. And step 2 transforms external input data into solver-ready format. Step 3 generates the formal specification from the structure description. And step 4 solves the model using the generated specification and the solver-ready data. If it compiles, we have the solution. If it fails, we send the specification and the error message from the solver back to step 3 and refine up to 5 times. Here we present a prototype of our approach for Kinaxis Maestro. Let me play the video. Okay, the planner starts from a workbook that contains the relevant data. She describes a production planning problem in natural language for 2 products, FGA and B. The agent reads the workbook and converts the description into a structure optimization problem. It identifies the objective, decision variable, constraints, and parameters. Here, the objective is to maximize total revenue while respecting available components inventory. After the planner confirms the structure problem, the agent generates the AMPL model, compiles it, and runs the solver, and returns a solution. The first solution has an objective value of 19 and recommends producing 6 units of product A and 2 units of product B. The agent also provides downloadable artifacts such as AMPL model. The planner then asks for a change, add the component purchases under a budget. The agent updates the structure problem, adds purchase decision variable, revises the constraint, and solves the new model. The new solution has an objective value of 140 and recommends producing 14 units of FGA with additional purchases of component X1 and component X2. Yeah, the analyst can compare the models, generated models. Next, the planner asks to minimize holding costs. The agent revises the model again. The objective now maximizes sales revenue minus the holding cost of unused components. Okay. The final solution is optimal with an objective value of 140. It recommends producing 9.5 units of A and 3 units of B with purchase of component X1 and X2 and 0 holding costs. The demo shows how the agent supports an iterative optimization workflow. The planner starts from workbook data and natural language description, asks what-if questions, reviews the structure problem, and revises the structure description, and receives a solvable AMPL model with solver results and downloadable artifacts. Now I will walk through the exhaust workflow step by step. The process starts with natural language description of an optimization problem, which is the input provided by the user. Step 1 is about structuring the natural language problem description. In task 1, the LLM extracts the objective or objectives if there is more than one. The prompt guides the LLM to identify what the problem is trying to optimize, such as maximize revenue or minimize cost. In our production planning example, the objectives are to maximize total revenue and minimize inventory cost. In task 2, the LLM extracts the decision variables from the problem description. These are the quantities that the optimization model needs to decide. The prompt guides the LLM to identify decision variables, including their symbol, definitions, and dimensions, such as the number of units to produce for each product. And in task 3, the LLM extracts the constraints from the problem description. Constraints define the the limits or rules that the solution must respect. The prompt guides the LLM to identify each constraints. In our production planning example, one constraint ensures that the required components for production do not exceed the available inventory. In task 4, the LLM extracts the parameters from the problem description. Parameters are fixed input values used by the optimization model. The prompt guides the LLM to identify each parameter, including its symbol, definition, and dimension, such as product prices, component inventory, purchase cost, or holding cost. Step 2 transforms the input data into solver-ready format. In industrial settings, the data needed for optimization is usually stored outside the problem description, for example, in workbook tables or databases. Exos uses the parameter metadata from step 1, such as parameter names, definition, and dimension, to connect each parameter with the right data source. The output is a solver-ready data. For AMPL, this is generated in AMPL-compatible data format, that file. And for Python, the data is generated in JSON format and passed to the solver code. Step 3 generates the formal optimization specification from the structure description. Depending on the target language, the output is either an AMPL model or Python code. The prompt gives the LLM the structured problem description, target language instructions, a guideline how to generate AMPL or Python code, and few-shot examples. If step 4 reports a compilation or runtime error, step 3 is called again. In that case, the prompt also includes the previous specification and solver feedback so the LLM can revise the model. Here is an example solution. The system returns production quantities, resource purchases, revenue, and holding costs. We evaluate Exos on 2 data sets. The public data set contains 60 textbook optimization problems, and the industry data set contains 6 real supply chain cases from Kinaxis. All problems are linear and single objective, and each has a ground truth solution, objective value. We evaluate 2 metrics, executability and correctness. Executability measures whether the generated specification compiles or runs successfully to produce a solution, to generate a solution. We report number of execution, success rate, compilation error, and runtime error. Correctness compares the generated solution with ground truth, the objective value. And we report a relative error and count of 0 error cases, a number of 0. Here, lower relative error is better, whereas a higher number of 0 error solution is better. We use for reasoning and instruction following LLMs from Vertex AI and OpenAI. The approach was evaluated using 8 distinct variants. Each variant is defined by 3 choices. The specification language, AMPL as a DSL, and Python code. Second, structuring, whether step 1 is applied to natural language description, and refinement loop, whether the feedback cycle between step 4 and step 3 is included. Here, AMPL 4 and Python 4 include both structuring and refinement loop. We use 66 problems for LLMs and 5 runs to reduce randomness. The number of generated optimization specification is over 10,000. For research question 1, we compare AMPL and Python on 2 metrics, executability and correctness, using Z-test and Man-Whitney U-test. For executability, the main result is that when we use a structured description and iterative refinement, AMPL performs better than Python. And for correctness, under the same setting, Python is not consistently better than AMPL. In some comparisons, AMPL is even more accurate. So with structuring and refinement, LLM-generated AMPL models can match Python code and in some cases outperform it. In research question 2, we analyzed the impact of structuring on the executability and correctness of LLM-generated AMPL models and Python code. For executability, AMPL with structuring outperforms AMPL without structuring, while Python shows inconsistent gains. And for correctness, both AMPL and Python with structuring match or outperform their no structuring versions. So structuring the problem description improves executability and correctness. For AMPL, for Python, the benefit is less consistent. AMPL benefits more from structured input. Here's the impact of the refinement loop for both AMPL and Python. Variants with refinement either improve executability and correctness or match versions without it. We also compare reasoning and instruction following LLMs across AMPL and Python. Reasoning LLMs either improve executability and correctness or match instruction following LLMs. Here are the best results, which come from structured description, refinement, and reasoning LLMs. We have detailed results for each research questions, including a statistical test. The results are discussed in the paper and are available online in the repository. These charts compare AMPL in orange color and Python in blue color for public and industry dataset. Average over the two reasoning models, O4 Mini and Gemini 2.5 Pro. On the left is success rate. AMPL reaches about 95% success on public and 80% on industry dataset. For Python is around 80 on both. And middle is zero error solutions. AMPL is higher on public, and both are essentially the same on industry, about 19. On the right is relative error. Errors are similar on public data set. Is a bit and Python is a bit lower on industry, but the gap is small and not statistically significant. Overall, AMPL is better in executability and competitive in correctness. In our experiments, there was no human in the loop, no user feedback on structuring or on the solution. And as you can see, the results are already really good, and we are confident that the success rates will be even higher if we have human involved who can provide feedback to the agent on the intermediate structured format. For the baseline, we compare Exos against prior work that targets Python code generation rather than AMPL like DSL generation. The baseline generates Python code from natural language description, and it keeps structuring and refinement, but omits our data handling step, which is one of the key differences from our approach. Also, this baseline is evaluated only on the public data set. In this chart, we compare baseline with the two best Exos variants under same structure and refinement setup. The results is that AMPL performs best overall. It reaches 95% success. It also gives the highest number of zero error solution, about 184. For relative error, AMPL and Python are almost identical, same. So the key message is that when Exos adds its explicit data step and keeps structuring and iterative refinement using reasoning LLMs, AMPL achieves the best results of executability and correctness. Python is close to the baseline, while AMPL outperforms it. Here are the main lessons learned from evaluation. First, it's important to keep data separate from the problem statement. Second, structuring the problem description. Third, the refinement loop is useful because solver feedback can help repair generated specifications. And finally, reasoning LLMs performs better than or on par instruction following models. To conclude, the idea is transforming a natural language description and its data into executable optimization model. Exos address this by structuring the problem description, keeping data separate from the model, generating a formal specification, and refining it using solver feedback. The output can be either an AMPL or Python code. In our experiments, AMPL models generated with structuring and refinement executed reliably and match or outperform Python in several comparisons. There are several next steps for this project over the next year. First, we plan to perform a qualitative error analysis to understand where the generation errors come from in the models. Then, based on those findings, we want to design automated repair methods that can detect common modeling errors and fix generated optimization models more systematically. Based on this analysis, we want to develop an error taxonomy for constraint modeling and DSL-related errors. These steps will help us improve the reliability and accuracy of the generated optimization models. Thank you for joining us today and for your attention. The implementation and experimental results for the public data sets are available online, and I would be happy to answer any questions.
Right. Thank you, Negin. Thank you, David.
Thank you so much.
We invite our audience basically to include any questions you have in the Q&A panel. It can be regarding some specific point of the presentation. It can be regarding a more general discussion. While our audience starts sending the questions, I want to start the discussion with an important conclusion I think you guys showed there, and is basically separating data is basically non-negotiable in industrial scale, because it always performs better, this LLM formulation, while separating the data. We agree with that philosophy. I think AMPL has strong features designed specifically for that. My question concerns modern APIs. So, for example, we provide a modern AMPL Py API, which does not affect the model formulation. So the model and the domain-specific language part of it remains. But maybe for larger data sets and for more large-scale problems, we may connect the data through this API or through this kind of Python code. So the question is, do you think, or if we were to try this modern API, the results would change dramatically? It would be more complex to write this code, or instead, on the contrary, it would be easier because now it doesn't have to learn that syntax. Like, how do you expect these types of things to perform on the Excel's development?
Yeah, that's very good points. In our design, the main goal of the LLM is to generate the optimization model. So moving from that first to an API such as AMPL could reduce the need for the LLM to learn AMPL data type syntax. It could simplify the workflow if the data binding layer is mostly deterministic. But the names and dimensions of sets and parameters in the model still need to match data passed through the API, I think. This is where the extracting parameters and adding metadata from the structuring step is useful. It gives explicit names, description, and dimension for the parameters and variables, which can guide the mapping between the model and the available data. The LLM could identify the required parameters and their dimension, while the software layer could verify that the corresponding data objects exist. The dimension match and the values can be passed correctly to AMPL using AMPL Py. So yeah, I would say that APIs such as AMPL Py could simplify the syntax side of data handling, but they do not remove the need for data and model matching, parameter names and dimension of parameters in data and model should be matched. Yeah.
Right. Thank you, Negin. I don't know, David, if you want to add something to it.
No, that's good. Negin, I think answered that well.
All right, yeah. Um, all right, I guess my next comment or question would be we've seen in industry there are many cases where you already have a large scale formulated model, and maybe this is not so focused on formulating but on explainability. So I guess how could the sales platform be modified not to like formulate the model, like which steps would change, but to provide some debugging if my run failed, or explainability of one solution that I want to understand better. So it's more a focus kind of change, but I was wondering if this type of workflow, the one Excel executes, can be adapted to this other goal.
Yeah, that's very good question, and it matches what often happens in industry. For existing large AMPL models, I would adapt exos instead of asking the LLM to regenerate the whole model. The system should first like analyze the existing model structure, identify its sets, parameters, variables, objectives, and constraints, and then localize the part related to the requested change. After that, the LLM should propose a small patch rather than a full rewritten model. The solver feedback could still be used in the refinement loop. The loop would be operate on the modify model. Another useful direction is to combine this with agent skills. For example, for each existing model or problem family, we could define a skills that capture the model structure, data assumptions, and examples of safe edits, naming rules. These skills could be loaded when the agent works on that model, the existing models. So the LLM is guided by model-specific knowledge rather than only general AMPL syntax. Yeah, so the adaptation would be to move from generated a complete AMPL model from text to understand, localize, and propose edits to an existing AMPL model. Agent skills could support this by giving the LLM reusable model-specific knowledge and editing rules. This is my answer. If David have other points.
Yeah, maybe in different industries, you have different data structures, different databases, if you will. For example, in supply chain, there's different measures, data that are known. The better those can be described, I think the better the system could work in terms of matching users' intent with solving creating a business optimization model for them.
Right. Yeah, I think we got a question from the audience. Igor is asking if do you have programs to use the tool for teaching a class in a university? How does the LLM tool license work together with AMPL Solver academic licenses? So I guess I'll give the run to you, but I remember you. I saw the repository, and I think that could be used, right, Negin?
Yes, we have online repository. The approach and all uh, is include a public data set, not Kinaxis data set, but yeah, we have mm, materials in the online repository. I think they ask about programs to use the tool for teaching a class in university. Yeah, you can use this approach. The tool is available in online repository.
Yeah, I think part of the question is the license type of thing. So to use the tool, do you need like some API key for the LLM, or yeah, how in terms of
They need
licensing, how it works?
API. Yes, they need API from OpenAI or other platform and LLMs family. They can use, they can edit the config file. There is a configuration file. They can use this configuration to add their API key and use this tool. Yeah.
Awesome.
I think Negin as
Yeah,
well.
and
Sorry.
Yes,
yeah, yeah.
David.
Oh, I was just going to add, I think for some of the other technology you used, Negin, there were academic licenses, like for the solver, for example. You were able to get an academic license for that.
Yes, yes, for Solver
Yeah,
and
I
using
was
AMPL and Groovy, I use my academic license. Sorry, Juan. Yes.
no, no. I was gonna press on that basically that AMPL provides
Mhm.
yeah, free license for all these also provide academic licenses. The LLM question, if the license for the LLM is free, I don't know. I don't think they have an academic type of thing. I don't know if when performing this you had some access or you basically had to get funds to try.
LLMs are not free actually, but um, I myself use academic license for AMPL and Groovy. Yeah.
Yeah, for the
All right.
LLMs, I believe Kinaxis had relationships with different vendors as well. For example,
Yeah.
we had access to Google's Vertex AI, which provides all kinds of tool access for AI, including access to Gemini. And so there were some things that we provided to University of Ottawa to so that they can have access to some of those models.
Yes, I use Kinaxis subscription using Vertex AI LLMs. Yeah.
All right. All right. Let me turn things over to more user experience. So more towards David. So first, and a specific question is more or less how much time did this test took? Like I know there are 10,000, more than 10,000 instances, but like in average, one question, the one from the video, for instance, how long does it take the tool to give or to provide the model formulation in average if you have that number?
Yeah. Yeah, so I don't know the exact number, but I'll share how we might think about that as a practice when thinking about design. So the thing for sure is that every user of software wants the numbers, the agents to work faster. That is a guarantee. And there's two different parts. So there's the part that Negin was doing to test and develop the system. And that was a lot of tests. An academic paper that she was working on needed to support that. There were tens of thousands of runs. But that's not what we'd expect when somebody's actually sitting in front of the software using it. That's more like the design and development time. At the runtime, when the user's asking questions, there are different approaches. Like if I were to use OpenAI's professional mode for their ChatGPT, every question I ask, it takes 10 minutes to come back. But what they do is they'll provide updates to the user about what they're doing. So there are different design techniques you can use to help the user understand that you're still working on the problem, that it's going to come back. But some of these answers, if you were to do them by hand or on a calculator, it would take you years to do it. So users, businesses understand that it can take a while to get the right answer, and sometimes that's worth waiting for. But there are UI techniques around making the software so that as people are using it, they understand that the system is doing something really like heavy lifting and doing something important for them.
Right. Thank you, David. Negin, if you have something to add.
The answer David gave us was complete, and yeah, that's very nice.
Yeah, yeah. I have another question because in the presentation you showed an example that had actually a multiple objective type of thing, and I was wondering if the tool can handle this type of thing. So in general, there may be two ways of doing multiple objective optimization, or the most known are basically doing hierarchical approach, where basically you solve for one and then you add that into the objective of the next solve, changing the objective. The second one is basically a blended approach where you add some weights, and that could have a lot of problems then. But My question is, how does Exeos handle this, basically?
Yeah, in our dataset, all problems are single objective. I use multi-objective for the example, but the approach can handle it in a second way using weighted some of objectives with weighted. Um, Thus, we add in the prompt and ask LLM to handle such problem like this. Yeah, but all problems in our dataset are single objectives. So, actually, yeah.
All right, yeah. That's an interesting
Yeah.
kind of thing to
Yeah.
explore. Yeah, well, I don't know if we are almost at the end of our time slot. Basically, we had 45 minutes. So if anyone has an additional question that they would like to send, please feel free. You're welcome to do it. Yeah, I guess I can keep with an additional question I had. I just don't want to kind of yeah uh, hold the questions there. So the research was from 2 years ago, right? So this started 2 years ago. So you tested mostly GPT and Gemini families. Uh, yeah, basically now we are seeing other players with LLMs like Cloud, and we are seeing increasing versions that has kind of built-in reasoning capabilities. Uh, do you expect that you show the table where you had the refinement loop, which is basically different version? Do you expect the results to change with like new models or new version of the models came in? So basically, AMPL 3, I think, was the one without the refinement loop versus AMPL 4, which is the one with the refinement loop. Do you expect that to change with new versions of these LLMs?
Uh, I cannot claim this with certainty without repeating the experiments with the newer models. But my hypothesis is that refinement would still remain useful even with a stronger reasoning models. The reason is that refinement gives the model access to solver feedback, which is very valuable. So we would still expect AMPL 4 with refinement, which include refinement to improve executability compared with AMPL 3. A stronger model may reduce the gap between AMPL 3 and AMPL 4. A more capable model may generate a better one-off model, so AMPL 3 may improve. But I would still expect AMPL 4 to perform better overall because it has an additional source of information, feedback from the solver. This feedback connects the generation process to the actual execution results. Yeah.
Maybe if I could add, so
Yeah.
one of the things that we observed was that there's a lot of change if you're in the AI space. Models are changing all the time. That was a bit of a challenge for us. So I think we had to lock in on specific models to do the research and to complete it. Otherwise, you'd be just continuing as the new models come out.
Yeah.
And I think we actually did see, like around as we were getting started, reasoning models started to come out. We noticed a big jump there. It wouldn't I like Negin's answer. We need to test it to be sure. But my guess would be that things would start to even continue to improve better with the better models coming up.
Yeah.
Great, thank you both, Najin and David. I think we are
Thank you.
on the edge of the limit, so I'm gonna thank you both, David and Najin, for your time and your explanations. I think this is quite an interesting research. Actually, we nowadays is not only enough to have a good modeling language, but a good modeling language that also plays good with today's tech stack, meaning AI, LLMs, and all this generative new stuff that's coming out. So I think this type of research helps a lot showcasing which tools and which parts of these tools we have to focus on. So thank you both for the presentation. And if anyone else have additional questions, they can send it to us. We probably share them with you. We'll also be sharing the presentation and uploading the recorded session to our YouTube channel.
Very
Yeah,
awesome.
thank you so much. Yeah,
Thanks for the
thank you.
opportunity.
And thank you for I would like to thank my supervisors. I know they are in participants, Mike and Shiva. And for David, David supports us during this project a lot. Thank you.
All right. Thank you all and have a good day. Bye bye.
Thank you.
No problem.
Bye.